Hey, welcome to assignment 6. Um, yeah, that'll work. 1 to 2, 2x dx. So, I want to, I want to consider something. I want to consider finding this integral, and of course, I feel pretty comfortable thinking about 2x going from 1 to 2 is this area, and I can find that area by saying, hey, let's find the area of that trapezoid. 1/2, the height is here, 2 minus 1. Base 1, well, if I plug a 1 in there, I get 2. And base 2 is this here. If I plug a 2 in there, I get 4. So I've got 1 times 6 times 1/2. 1 times 6 times 1/2. Did I miss something? 2x. 4. Sorry, my note says something else here. I think my note is wrong. So I'm wondering, why is my note wrong? But we end up with this integral equals 3. Okay. Well, now I kind of want to say, how do we do this without appealing to the geometry of the situation? Okay. So what can we do there? Well, we know that this is the derivative of something. What is it the derivative of? Well, it's the derivative of x squared. But remember, we had that thing show up both in Chapter 3 and in Chapter 4 that said, well, there's lots of different functions that have this derivative. So we've got in the habit of saying that with our antiderivative. Whenever I'm doing an antiderivative, whenever I'm going backwards, I've got to have that plus c. Okay? And one way to think about that is, if I have x squared plus 4, then y prime is 2x. But if I have x squared minus 7, then guess what? Y prime is still 2x. So functions that have the same derivative differ by a constant, or could differ by a constant. So here, I know the antiderivative of this, going backwards, is going to be x squared, but I've got to have that plus c. And what I'd like to consider is, how do I go from this integral to this answer without using geometry? Because I'll tell you, most of the stuff we do in calculus, I can't appeal to the geometry of the situation. When I can, it's great, but often I can't. So let's see if we can build that conceptual bridge. What will get me from this to that on the interval from 1 to 4? Think about it for a minute. No, don't give up yet. Keep thinking about it. I want to use this function to generate this answer on this interval. Do you see it? Yeah. 2 squared is 4. 1 squared is 1. 4 minus 1. 3. And so what we're going to say here then is that if I evaluate this antiderivative, which is often called big F, as opposed to what's over here, which is often called little f, but not always, so we'll be more clear. So I think what I want to do is say that f of 2 minus f of 1 is going to get me that number. Okay? But, yeah. So f of 2, 1, I plug a 2 in here, I get 4 plus c minus, and I plug a 1 in here, 1 plus c. And notice what happens. We distribute that negative, and then we have minus c as well. And so the c's always cancel, and we're left with 4 minus 1, or 3. So this mechanism, where we use the antiderivative to evaluate the integral, that's what we're going to be doing a lot of. Okay, so we'll be seeing this. If I have the integral from a to b of f of x dx, I know that's going to be f of b minus f of a. Okay? And we'll dig more into this very shortly. But for right now, that's my understanding where big F prime equals little f. So if I take the derivative over here, I'm getting this thing. The antiderivative of this gets me back here. Yeah? Okay. So we can use this information to evaluate not only things like the integral from 1 to 2 of 2x dx that we just did, but what about this one, the integral from 0 to pi over 2 of cosine x dx. Great. So what do? Remember, integration is anti-differentiation. I'm going backwards. So I'm looking at someone's derivative. Whose derivative is this? Okay, so I say that this is sine's derivative, and I want to evaluate that from 0 to pi over 2. Remember, we want to evaluate the antiderivative. This is big F, the antiderivative, at both this place and this place. So I've got sine of pi over 2 plus c minus sine of 0 plus c. Well, that's going to be 1 plus c minus 0 minus c, and we end up with 1. So my integral here is 1. I can't appeal to this geometry. You know, I know what that graph looks like. I know what it looks like from 0 to pi over 2. It's not for a lack of knowing. It's, I don't have a geometric shape there that I can use. And so instead I'm going to, be using my antiderivative to help me to evaluate this. Okay? And this is why it's so terribly, terribly important for you to be comfortable with all your derivatives. Because now I'm going to say, hey, what's the integral from 0 to 1 of 1 over x squared plus 1? Do you remember whose derivative that is? If you don't, you need to be honest with yourself and say, damn, I better start practicing those derivatives again so that I remember, or at least review them. No, really, because everything depends on you knowing those derivatives so you can find the antiderivatives. You're supposed to recognize that this is inverse tan's derivative. So I've got inverse tan x from 0 to 1. Okay? Great. Now, hold on, there's more. I'm supposed to evaluate this at those two places. Did you notice that I didn't do the c's? Yeah, so here's what happens. If we've got the integral of f dx from a to b, and we know that big F prime equals little f, then we can say big F of b minus big F of a. But remember, when we do that antiderivative is going to have a plus c. But always the plus c on this one and the minus c on this one will cancel. So I give you permission, very specific permission. Don't abuse it. When you have an indefinite integral, 1 over x squared plus 1 dx, indefinite, no boundaries, that has to have, that must have the plus c. If you have a definite integral, an integral with boundaries, the plus c and the minus c, they're always going to cancel. You don't need to put it. You can go and just evaluate the antiderivative. Okay, last cautionary tale about this one. Students stop here. And while sometimes it's okay to stop, like if I saw the integral of 1 over x dx from 0.7 to 1.3, then I would say, oh, well, that's ln of x evaluated from 0.7 to 1.3. And I would say that's ln of 1.3 minus ln of 0.7. And no one expects me to do anything with that. Okay, not if it's not with calculator, then I stop here. However, with this problem, we are expected to know these values. We are. Inverse tangent of 1. What angle has a tangent of 1? And remember, what angle within the restriction for inverse tangent, i.e. negative pi over 2 to pi over 2. So when is tangent 1 on negative pi over 2 to pi over 2? At pi over 4. What angle within the restriction for tangent has a tangent value of 0? Well, the tangent of 0 is 0. Remember, tangent is sine over cosine, and I want that to be equal to 0, which means the top has to be 0. When is the sine function equal to 0? On negative pi over 2 to pi over 2, and that happens at 0. So this integral is going to be pi over 4. Right? No, really. You have to know your derivatives so you can go backwards, but you also still need to retain some of your trig and pre-cal knowledge. And if you don't have it, don't hide from it right now. You need to step up and start dealing with it. Okay, so that's a whole lot of stuff. I think I just want to do 2 more things with you. I want to do a quick review of integral properties, and I say I want to do a quick review because most of you are going to ignore these. Just like when you were in middle school, you ignored the commutative property of multiplication, and then it turned out, oh my goodness, I always get the problem wrong when I don't use the commutative property of multiplication. Like if I see, yeah, no, I'm not going to go there. Sorry, I want a commutative property of addition to say 3 minus square root of x. And, I want you to graph this thing. Well, it's hard for people to think like this, but much easier for people to think like this. Oh, I multiply the y's by -1 and add 3 to them. So I had to use the commutative property of addition. And so just like that was like something your 7th grade teacher tried desperately to help you see, so too, I could spend a lot of time trying to convince you that these integral properties are terribly, terribly foundational and important, but most of you will just say, oh yeah, I kind of, was going with that anyway. So here's our first one, the integral of a constant. We talked about this. We know it's always going to be a rectangle whose length is b minus a and whose height is c, and so we're just looking at the area of this rectangle. All right, there's integral property number 1. Number 2, the integral from a to b of f of x dx. Well, guess what? That's actually equal to negative the integral from b to a of f of x dx. And so what this is saying is that, well, for example, we're accustomed to this number being smaller than that number. And now we have this situation where this number is bigger than that number. And so I'm thinking about not integrating this way, but instead integrating that way, from the bigger number to the smaller number. Well, that's going to be the opposite, the negative valued answer to if I went from smaller number to bigger number. So if this area is 4 when I integrate this direction, if I integrate in the opposite direction from here to here, if I integrate this way and add up all these, it turns out this is a negative length. These are all still positive, but this is negative because I'm headed that way. And therefore, my area turns out to be negative. And so my area will be the opposite of what it was from A to B. Okay? Again, when we need this, there it'll be for us. Okay, integral from a to b of f of x plus or minus g of x dx. Well, I actually used this in the last video where I said, hey, let's split this up, a, b, and none of you caused a fuss when I did it and said, can you really do that? Or at least you didn't say anything to me about it. Maybe you were like, how the hell is he doing that? So this is what we know. We can take an integral that's a sum of functions and split it up into 2 or 3 or more different integrals where we integrate just each of those pieces that are being added together. Now, caution, we do not have a property for this. This is going to be a very special and different situation. We'll definitely be doing it, but not here. So no, this one, a to b, f of times g, is not going to be the integral from a to b of f times the integral, don't lose that dx, from a to b of g. Okay? All right, so not equal, not equal, not equal. Not just pool noodle chases you, but Dr. Seuss's Snickberry switch. Yeah, okay. So we've got that rule. It's very handy. So that allows us to take something like 2x plus 5 dx and then say, oh, well, that's just the integral of 2x plus the integral of 5. And we know this is x squared, and we know that this is 5x. And don't forget, when you go backwards, have that plus c. Okay? So we can split one integral into a bunch of pieces. Woohoo! All right, next one. What about the integral of a constant times a function? I don't have a property for function times function, but I do have a property for constant times function. And it turns out what I can do is pull out that constant and integrate just the function, just like derivatives, right? The derivative of c times f of x was, let's pull off that constant and then just take the derivative of this. And I'm saying something analogous here, which is, hey, you've got a constant times a function. Great, pull that constant out, integrate the function, and then multiply the two together. Okay? All right. What's next? Oh, this one. Yeah, this is a great one. AP loves this one. The integral from a to a of f of x dx. Now, let's think about that graphically for a moment. I've got this f function. Here's this point, x equals a. And I want to integrate from this point to this point. Yes, that's right. From that point to that point. Well, so what does that mean? Well, that's big F of a minus big F of a. A number minus itself is 0. So my integration, when I go from a to itself, is always going to be 0. Because Euclid says a line, a point, these things take up no space. So that width that I'm drawing with my pen, yeah, it exists here, but not in mathland. In mathland, this has no thickness, this just from a to a. So we're finding, a rectangle here, and the rectangle's width is a minus a times the height of the function at that point. Well, a minus a is 0, so it doesn't matter what the value of that y value is. I've got 0 times a number, I still get 0. So integral from a to a is 0, and you will use that a surprising amount, especially in challenging problems. Okay, I think it's the last one. No, we have 3 more. We've got the integral from a to c of f of x dx. And so here's my function. Here's a, here's c. And what I want to say is, I could actually have this b, and I could say, well, the integral from here to here is that area plus that area. The integral from a to b of f of x dx plus the integral from b to c of f of x dx. So it's kind of like the transitive property, if a equals b and b equals c, then a equals c. It's not at all the transitive property. And all of those math degree people right now are really throwing rocks at me. So don't say that in public, but yeah, it's kind of like that, metaphorically speaking. Okay, so those are the ones that we need to be comfortable with. Now, there is 2 more, and yeah, so this one is called max min. And max-min, it's kind of like a RAM. What we're saying is we've got some sort of function here. And this is 2, and this is 1. And what we're going to say with max-min is that this area under this curve, yeah, why do I need this? Well, here's the deal. You remember how we use the antiderivative to evaluate the integral? Well, there are some functions that we can't algebraically make the antiderivative for. I'm sorry to have to break that news to you, but not everything we don't have a way to find the antiderivative of everything. So the best I'm going to be able to do is say, well, I don't know what this area is, but I do know that this area is smaller than this area, right? So I'm saying, well, I don't know what the area from a to b of little f of x dx is. Here's the f of x. But I know that it's got to be smaller than, could be equal to, I guess, not in this picture, but smaller than the maximum y value on f, which conveniently happens here at this endpoint, but it doesn't have to. You know, we could have drawn something that went whee and back down again. And in fact, let's use that. Okay, we're saying that this area is smaller than this rectangle's area. Okay, and what I'm doing with this rectangle is saying, well, what would the area of this rectangle be? It's got a height of 1, which is really the height of the maximum. So I kind of want to say that's c f of c times this length here, which would be b minus a. Okay, so there's our max. Our maximum times b minus a. That gives us this big rectangle, and this area underneath it definitely is smaller than that. But I kind of want to squeeze this area in by using also the minimum value. Okay, so here's my minimum value. Let's say it's 1/10 there. I'm going to say the value of this integral is definitely bigger than this tiny rectangle here. So this integral is greater than or equal to, we have a height of 1/10, the min y value times b minus a. So I'm saying this area under the curve is an area squeezed between a minimum, the minimum y value on that interval, minimum times b minus a, and the maximum y value times b minus a. So we're squeezing our area in between these two rectangles, this big one and this little one. Sandwich theorem. Yeah, it's kind of sandwich theorem, huh? Okay, but max-min. So, and then the last one, you know, has a cool name. It's dominance. And you can have my permission to use the exclamation point there. But dominance is really kind of an obvious property. Like many of them, you know, feel very intuitive. Maybe not that last one until I think about it some more. But most of them have been pretty straightforward, and I don't have a lot of, you know, concern about them. But if f of x is always greater than or equal to g of x, so here's a situation. There's f of x. There's g of x. F of x is always above g of x. They could touch, could be equal to, but right now we're saying f of x is bigger than g of x. So then, here's dominance. A to b, f of x dx is going to be greater than or equal to a to b, g of x dx. And don't you just want to say, duh, if this curve is always above this curve, then that area is definitely going to be bigger than that area. Yeah, for sure. So, yeah. Uh, I'll use it, but yeah, yeah. Okay, so let's do some practice. You need to be fast with these. Okay, so practice. Minus cosecant squared dx. Notice we're doing an unbounded. It's not a definite, but an indefinite integral. So let's see how fast we can go. What's the antiderivative of negative cosecant squared dx? 5, 4, 3, 2, 1. No, really, that fast. You really need to say, oh, I recognize you. You're the derivative of, who is this the derivative of? Cotangent. Don't forget the plus c. Okay, here we go. Cosine x dx. 5, 4, 3, 2, 1. Did you say sine x plus c? 3. Negative sine x dx. 5, 4, 3, 2, 1. Whose derivative is this? This is cosine's derivative. Okay? I need to know my derivatives. I can't go backwards without knowing my derivatives. Now, what about this situation? The integral of negative sine x dx. How are you going to think about this? I've heard a number of different ways to think about this, but I want to know how you're going to think about this. What is that antiderivative? Whose derivative is negative sine? Cosine's is. Now, think also, did I just, oh, we just did the same problem twice. Sorry, sleepy Googler still. That's the one I want. The integral of sine. Whose derivative is sine? And that's negative cosine plus c. And some people are able to say, oh, I know when sine shows up. Sine shows up when I'm doing the derivative of negative cosine. Yeah. But you know, you could also think about it this way. You could say, well, how about cosine? Is cosine the antiderivative? Well, if I take the derivative of cosine, I get negative sine, and I don't have a negative here. So there must have been a negative present in the original situation, so that when I took the derivative of this and said, okay, the derivative of cosine is minus sine times minus gives me positive sine. Yeah, so one of the things I'm going to recommend is that when we're doing these problems that are related to derivatives, I mean, maybe I should know the derivative of negative cosine, but I don't quite recognize it. Yeah, I can often think about these by thinking about what must be there so that when I go backwards, when I go forwards and take a derivative, the stuff I want is there. So, for example, if I see 2x dx, I think, oh, well, you're the derivative of x squared. Don't forget the plus c. But what if I see something like, that's coming. Okay, what if I see something like this, right? I know that the antiderivative is I have to add 1 to that. So I think, okay, you're x squared. But look, if I take the derivative of this, there's going to be a 2 in front, and there's no 2 here. So where did the 2 go? Well, when I take the derivative of this original function, that 2 is going to come down. So there must be something here on the original function so that when that 2 comes down, it cancels out. The 2 comes down for the derivative, cancels that, and leaves me with that. Now, for a power rule, we could say something like, okay, the integral of x to the n dx is going to be x to the n plus 1 over n plus 1. That's what we just did, right? We had x to the first, so we put x to the first plus 1, which is x to the second, over 1 plus 1, or 2. So you can use that here with the power property, with the power functions. But that can't necessarily do the same thing with all the other types of functions. So yes, that's nice, but I think more generally, when you're going backwards, always think, well, if I take the derivative of that thing, will I get back to where I want to be? And the answer is probably, I need to practice that some more, Mr. Kukla. So how about this one? The integral of 4x squared dx. What are you going to do here? 5, 4, 3, 2, 1. Now what I want to know is, how many of you did this? You pulled out the 4, you integrated x squared to make it look like that earlier problem, and then you said, aha, so I'm going to use that n plus 1 thing divided by n plus 1. And then the integral of the function times the constant. So that's one approach. Another approach is to say, okay, so I know that x to the third is the antiderivative of x squared. And I know that that 4 is there. But if I take the derivative of this, that 3 is coming down. 3 times 4 is going to be 12. I do not see a 12 here. I see a 4. So what must happen? Well, when that 3 comes down, there must be something present in the original problem so that when that 3 comes down, it cancels. And so I end up then with, this is my antiderivative. Okay? Another way to think about that? Not yet. I'll dwell on it some more. Okay, how about this one? The integral of e to the x dx. 5, 4, 3, 2, 1. Please don't forget the plus c. How about the integral of 2 to the x ln 2 dx? 5, 4, yes, this fast. 3, 2, 1. And you should know that as 2 to the x plus c, because remember, the derivative of 2 to the x is 2 to the x ln of 2, or the derivative of b to the x is b to the x ln of b. Right? You need to know this. You knew it last semester. So get that knowledge back. This is whose derivative? Whose derivative is that? It's 2 to the x's derivative. Okay, so what if I see this? See, I can't use that power rule here. You're someone's derivative. Whose derivative are you? Are you 2 to the x's derivative? Well, if I take the derivative of 2 to the x, I end up with 2 to the x ln 2. But there's no ln of 2 here. So there must be something present in the original function so that when I take the derivative of that original function and that ln of 2 shows up, it gets canceled. That's my original function, right? So I can write that as 1 over ln of 2 times 2 to the x. The derivative of 2 to the x is 2 to the x ln 2. That ln of 2, that ln of 2 cancel and leave me just 2 to the x. Okay? All right. Let's go. How about this one? The integral of ln of x dx. 5, 4, 3, 2, 1. I just went that fast because I wanted to see how many of you would say this. And that is so completely wrong. This is the derivative of that. But I'm looking for the antiderivative of that. This is someone's derivative. Whose derivative are you? You're not the derivative of 1 over x, or x to the negative 1. We know the derivative of x to the negative 1 is negative 1x to the minus 2. No. Whose derivative We'll find out in Chapter 7. For right now, though, whose derivative is this? 5, 4, 3, 2, 1. Excellent. ln of x plus c. Great. How about this one? Integral of 1 over x squared dx. 5, 4, 3, 2, 1. Now, this one's a little harder, and I understand if you were nowhere near being done when I got to 1. Think about this way. Okay? This is, that power function kind of thing. I can add 1 on top, and so now I'm going to have x to the minus 1. Right? So if I take the derivative, that minus 1 comes down, and I subtract 1 here to give me that negative 2. But there should be a minus 1 here when I take the derivative, and there's no minus 1 there. So what must be present in the original function so that when I take the derivative of the original function, I end up with this positive x to the minus 2? Well, that means there must be a negative there already, so that when I bring down another negative, negative times negative, gives me that positive out in front. Please don't forget the plus c. Okay, how about this one? The integral of 1 over x squared plus 1 dx. 5, 4, 3, 2, 1. Did you get tangent inverse x plus c? Yeah. Whose derivative are you? Your inverse tangent's derivative. What about this integral? Integral of square root of x dx. You may find it easier to write that as x to the 1/2 dx. 5, 4, 3, 2, 1. Remember, this is someone's derivative. Whose derivative? Well, are you x to the 3/2? I bring down the 3/2, I subtract 1. 3/2 minus 2/2 is 1/2. But wait, if I take the derivative, that 3/2 should be in front. I don't have the 3/2 down here in front. So there must be something present in the original function so that when you take that derivative, that thing that's not there goes away, cancels out. So I must have a 2/3 here. Okay, and so when I bring down that 3/2, I get that canceling, and I just have x to the 1/2. If you're thinking about, well, x to the n plus 1 over n plus 1, that's working too, because look, if I have 1/2 plus 1, that's going to be 3/2, and that's over n plus 1. That's going to be 3/2. Well, if I put a 3/2 down here, and I do that flip and multiply that Mrs. Rowan taught me about in the 7th grade, these turn into 1, and there's my 2/3. Okay? All right. So, can you do this one for me? The integral x to the 1/2 plus 1 dx. I mean, we know what it looks like. It's the square root of x graph shifted up 1. But this isn't a definite integral. It's just an indefinite. What's the antiderivative? Ooh, and we can use our properties. Okay. 5, 4, 3, 2, 1. I end up with 2/3 x to the 3/2 plus, what's the antiderivative of a constant? A constant times x. So 1 times x. Don't forget the plus c. And I bet you're thinking, Cuckoo, you can stop saying the plus c. I got it. Yeah, no. No, you don't. You only think you do. Oh, trust me. Okay, so what do we have going here? So sorry, that was a GroupMe chat. Give that one a try, and I will be right with you. Okay. So, did you end up with x to the 4/3? And what did you do? Because then that 4/3 comes down. There's no 4/3 there. That's right. That's got to be a 3/4 plus c. Okay. How about the antiderivative of 1 over square root of 1 minus x squared dx? 5, 4, I'll start again. Negative 1 over square root of 1 minus x squared. 5, 4, 3, 2, 1. All right, what did you get for that? It's the derivative of, now I'm having difficulty. There it is, cosine inverse of x. Don't forget the plus c. Okay. As opposed to this one. 1 over absolute x square root x squared minus 1 dx. Whose derivative are you? 5, 4, 3, 2, 1. Secant inverse of x. Don't forget the plus c. I know, I keep saying don't forget the plus c. You know why? Because even though I've said it this many times, we're all going to forget it at least once. So please, plus c, plus c, plus c. How about this one? The integral of secant x tangent x dx. 5, 4, 3, 2, 1. That's the derivative of secant. Don't forget the plus c. All right, and how about this last one? 2 to the x over ln of 2 dx. Please find that antiderivative. 5, 4, 3, 2, 1. Yeah, so how did you think about it? Like, let's think about just 2 to the x. What's 2 to the x's antiderivative? Well, remember, if I take the derivative of 2 to the x, I get 2 to the x ln 2. Well, I don't have that there. I've got an ln of 2, but it's in the wrong place. So I would need to divide by ln of 2 to get rid of it from the top, but then I would need another one so that when I took the derivative of 2 to the x, when I took the derivative of 2 to the x and that ln of 2 shows up, not only does it go away, but I have another one left over. So my original function is actually got to be 2 to the x over ln of 2 squared. And again, if you're not sure, and trust me, you're going to be not sure, you really, really should take the derivative of what you think the antiderivative is. Please don't use quotient rule here. Please think about this as 1 over ln of 2 squared times 2 to the x. And let's take the derivative of this. Constant times a function is going to be that constant times the derivative of the function. The derivative of 2 to the x is 2 to the x ln 2. Remember, though, times our constant 1 over ln of 2 squared. Those cancel. I have 2 to the x over ln of 2. Okay? Okay. Well, I hope this was helpful, and I look forward to seeing you soon. Take care, everyone.